Okay, physics time. Today we're talking about energy, which should be largely a review to those of you who are in class today. We'll just call it energy. Why not? What is energy? I'm gonna have I'm gonna get my energy demonstration ball of science out. Define energy for me? I don't want to hear the book's definition. I want to hear your definition. Energy is the ability to cause change. Energy is the ability to cause change. Energy is the ability to cause change. I'm really tempted to go into kind of like a philosophical diatribe about the importance of change. Because change is everything, isn't it? The only thing that stays the same is that things always be changing. Things always be changing. You know that you are a different person now than you were. Yeah, I don't know. 2 minutes ago might be a little bit brief, but I first met you, both of you, when you were in 7th grade. That was, what was that? 4 years ago. It went by like a blink of an eye. But you are, in every single way, different than you are now. What's different about you? What has changed? Your hair is different. You have different hairstyles. Some of you have different eyebrows from the way they were back then. Your bodies are bigger. They're different. They are made of completely different atoms, probably. Probably completely different cells. There's probably no one cell alive in you that was alive back then. I don't know that for sure. But even if that isn't true, I would say more than 99% of the cells that are in your body are different in essence than they were before. So what's you? What's you? What does it mean to be Lily? What is Lily? What holds you together? What makes you you?
That's very philosophical.
Well, what is it? Is the energy within you the same? No. Energy. So what I'm getting at here, I could go a different direction with that. I could really philosophize about that for a long time. But what I'm getting at here is that this is what we call the ability for that to take place. What provided this over all those years for you to change? Primarily, 3 things. Food. Water, yeah. Water is, I wouldn't say that water provides you any kind of energy specifically, but it provides the building blocks necessary for this energy to be transformed such that it can be used for other things. What other kinds of energy does your body use? Your body is a terrific machine at making this into this. That is to make the energy held within chemical bonds, in this case in your food, into the energy of your movement. Look at me. I'm doing a little talk, and so of course I'm moving, because I do kind of gesticulate, not very much, not as much as some people, and I wouldn't say wildly. I think that'd be really an overcharacterization of my attitudes if you said that I gesticulate wildly. But I do move when I talk, and what gives me that? What gives me the energy to be able to do that? Well, my food. The caloric energy that I intake. What if we think of my hand as an object, not the same hand I had when I first met you, but if I think of this hand as an object, and I move it from here to here, now it has some gravitational potential energy. And really, chemical energy is a kind of chemical energy is a kind of potential energy, of which there are several. Let's list them. Let's list a few. So, chemical potential, gravitational potential, and elastic potential. This would be elastic potential energy, right? If I pull it down like that and it kind of springs back up, that's elastic potential energy. There's energy stored within the bonds of this nylon that when I let go, the energy is released, and it turns it from elastic energy to kinetic and potential energy. This is the energy of movement, as we know. And this is the energy that could be. The energy that is, we oftentimes say, stored. Although that doesn't really fit the bill super well. Another way of thinking about energy is as work. W equals F cross D. All three vector quantities. W is work. F is force. D is distance. Directional distance. What do we measure distance in? What unit do we use to measure distance? Meter. What unit do we measure force in? Newtons. And then if we get this, we get a Newton times a meter, which is the same as a joule. Remember, a joule is a kilogram meter squared per second squared. A Newton is a kilogram meter per second squared. So if we have a kilogram meter per second squared times meter, we get kilogram meter squared per second squared, which is a joule. What's this little boy?
Rocks.
What's that mean? I don't know. It's not just multiply. What it is that we have to take the vector of, let me phrase it this way. Work can only be done if force and distance isn't, or sorry, work is only done to the degree that force and distance are in the same direction. Work is only done to the degree that force and distance are in the same direction. In the video, the strong man, the strong sweaty man, remember from the strong sweaty place? What's that place called? The gymnasium, yeah. And he was hoisting the heavy thing. Which way was he moving it? I mean, which way was the force acting when he put that force on it? Up. Which way did it move? It went up. Was work done? Yes, that's work. What if weak man comes along? Who should we use as weak man? I don't want to be that mean to anyone. Weak man comes along, and he tries to move it. He is putting a force on it, but it moves zero distance. Is work done? No. Work is only done to the degree that force and distance are in the same direction. So this crosses that we use vector math. Vector math. Let me give you an example of that. Here's your boy. Mowing the lawn. And the lawnmower is moving this distance. We'll say 10 meters. We'll say east. It doesn't really matter, but 10 meters east. And your boy is pushing down and to the east with a force of 390 newtons at an angle of, what would this be? Let's say, what would make sense? 340 degrees. Where 0 degrees is straight east, 180 is straight west, 270 is straight down, and this is at 340. So we can't use the whole amount of this force, can we? We can only use the what component of this? Yeah, the x component of this, the x component of this. So we use this. So if this is at 340 degrees, what is the angle down of east? If this is 340, what is this? No. Zero is also 360, so it's how much down of 360? 20 degrees. Okay? And I want to find, if this is my angle here, the 20, this double angle here. And this is not going to show up very well at all in the video. I should have done this here. I have like 3 words over here, taking the same amount of room as this nasty little diagram. But you can see it okay, right, in real life? I'm tempted to just redraw it. Oh! Okay. You already had this. You already had this. That was not a question. Okay. Lawnmower. It's one of them old-timey lawnmowers with the like razor blades up in there. Um, 10 meters east. We discovered just now that I am pushing at an angle of 20 degrees. Yeah, ya boy. Oh, sorry. Ya boy. We discovered that ya boy was pushing at an angle of 20 degrees down to the east. I want to find the x component, so f sub x will be this component. So what are we going to do? What's it called? Vector. Yeah, what kind of math are we going to use? Trigonometry. So we're going to have 390 degrees. I'm sorry, don't write that. Newtons times sine or cosine here? That was a question. There's two answers, or there's two choices. There's one answer. Let's try again. Cosine. Times the cosine of 20 degrees equals what's this going to tell us? I'd like someone to do it, but in the meantime, what's this going to tell us? What's this going to tell us for my question? My implied question, I never actually asked. The question is, how much work is being done? What's this going to tell us? What's the answer going to tell us?
It's going to tell us one of the sides, or the
Okay. Why do we care? The x component one.
direction in 3, 6.
Yeah, it's telling us how much. Remember, work is only done to the degree that force and distance are in the same direction. So work only this part, only the x component, because what's the x component of the distance? Well, the distance is all x. So if we're finding the x component of the force, that's going to tell us how much of the force is being applied to this. Is it going to be greater than, equal to, or less than 390 newtons? Definitely less than. Think about it as, if not your boy, but you yourself, y'all are mowing the lawn, is all of what you're pushing down and forward going forward? No, obviously not, because some of it's going down too. So, answer?
366.5.
367 newtons. How do I know it's newtons? Because that's what it was before. 367 newtons. So now we have W equals, the way we could have written this, I'm going to show you, 390 degrees, 390 newtons times the cosine of angle 20 times the distance, 10 meters. It's not always going to be cosine. Think about what trigonometric sign will actually get you in the same component as the direction. What's the answer here? Work equals 3,670 joules. How do we measure energy? What unit do we use to measure energy? Joules. You got it. Always? What's the English unit for energy? No, that's power, but that's a good, and that's also the SI unit for power. Let's think about it this way. How is your boy going to replenish this energy? Food. And how do we measure the energy of food? Calories. The English unit for energy, which some of you learned, this is not a joke, literally the last chapter we did in Chem 2 was about calories and joules. But that was also November, so they've gone a lot. Okay, so that's how we calculate work. Questions about that? This is the same as how we calculated work when you were in physical science, except instead of just the question, is work done? Remember we had that yes or no, depending on if it's in the same direction or not. Now it's to what amount is work done, and we use trigonometry. You can see why I don't show that to the freshmen. But you are already used to this, and you already remembered this from physical science. So you just put those two things together. It makes it really pretty easy. Power. A student who shall not be named, when I gave the test on this to the physical science students, the question was, define power, and the student wrote, I need more power. And it was really alarming to have that received as a test. How do we calculate power? The way I usually ask it, and this is a lab we do in physical science. We didn't do it this year because they're too chaotic, but you guys did it. When you walk up the stairs compared to running up the stairs, in which case do you do more work? Now think about it. Think about it. Which case do you put a larger force over a larger distance, for instance, or a larger distance? Is the distance different? No. Is the amount of force, that is your weight, different? No. So is a different amount of work done? No. But obviously one of those things feels different. So what is different about it? The power, the time, yeah. So power is the relationship between work and time. P equals W over T. Another way, P equals E over T. Why can we do this? What's E probably? P is power. E is energy. W is work. Remember, work and energy are the same thing. Work is energy that is done to move an object specifically, but it's a type of energy. And lowercase t, as always, is time. Measuring time in seconds, measuring work in joules, measuring energy in joules, we get joules per second, which is also a watt. That's an E. No, the bottom is a T. It looks like this. This is how I always make my lowercase t for time. Cute. Okay, anyway. To calculate this, we just divide work or energy by time, and that gives us power in watts. There are two kinds of energy that we also calculate. There are two kinds of energy that we calculate. What are they? And by that I mean there are two specific kinds of energy that we calculate. I'm going to, actually. What are the two kinds of energy that we calculate? You already know what it is. This is all mostly review. Yep. We're not going to spend very long on those because they should be review for physical science. U, potential energy, equals mgh. K equals 1/2 mv squared, where U is potential energy, M is mass, lowercase g is acceleration due to gravity, and H is measured in you're not wrong, I just don't want you to say that. Meters. Acceleration due to gravity measured in mass measured in kilogram times meter per second squared times meter is kilogram meter squared per second squared, which means potential energy is measured in joules. K equals 1/2 mv squared, where you know what 1/2 is, so K is kinetic energy, energy of motion. So it should depend on what quantity? Velocity, she means. Lowercase v is velocity, measured in meters per second, mass measured in kilograms. What do we do with the velocity, though? We square it. We square the number and the units. So we get kilogram times meter squared per second squared, which is, again, a joule. These questions are just plug and chug. You should be able to do them. They're also review. Capital K. Yep, capital K. Your book also discusses simple machines and efficiency. You know what those are. And it discusses mechanical advantage. You remember what that is too. All of those things are review. You should know the types of simple machines. If you need a refresher, I have, I think, 3 now physical science videos about it, and also your book tells you about it. And also, let me give you a hint, they're not super important on the test. The main things that we do in this chapter, as far as the test, is do know those things conceptually, but also this math, this math, this math, and work that I erased. Questions? I was going to do a demonstration with this, which is why I got it out. I'm going to do the demonstration. In fact, this is review, but I'm going to tell you anyway because I like this demonstration. What is it? It's a little ball. How did it get up here? I put it up there. What did I have to do to put it up here? I had to change something, didn't I? That's energy. What did I have to change? What did I have to change to get the ball here? I changed its height. I put it up here. What does it have? What kind of energy does it have sitting up here on my little paw? It has potential. Does it have kinetic? No, the particles that make it up do, right? Remember, particles are always in constant random motion, but we call that temperature. But this object, as an object, does not have kinetic energy. As I drop it, it's what kind of energy that it has right now? Potential. Slowly becomes, well, as slow as it falls, but it becomes, as it falls, the potential energy does what? It turns into kinetic. We could say it that way. We could say that the potential is constantly decreasing and the kinetic is constantly increasing. Notice of our 2 equations. Did the mass change? I mean, the mass can be whatever it needs to be in these equations, but for this object, did the mass on which they both depend, did that change? No. Does acceleration due to gravity change? No. So height is decreasing and velocity is increasing. Right here, all potential, no kinetic, you already said. Right here, right before it falls, right before it hits the ground, all kinetic, no potential. It has 0 height, so u is 0. And it has, the velocity is not infinite, but its velocity is as high as it will get, so its kinetic energy is full. This is called the law of conservation of energy. Now look at this. This is real life. This is math. Bogus. This is real life. If this were true, if this math were true, shouldn't it bounce right back up into my hand? Yep, but why don't it? Why is the real world different from the math? What are we forgetting here? Yeah, not just friction. Or forgetting about the ways that energy can be lost. What are the ways that energy can be lost? That is, remember, no energy can ever be lost, but energy can be spread out into the environment such that it's no longer useful. Let's list them. Heat, sound, deformation. Let's go from the bottom. Deformation is that some of the energy that was in this ball, if we were to watch this in slow-mo, you would obviously see the ball go. And some of the energy, that means, that was in this ball is now transferred to its, well, I mean, its particles already had energy, and this had as much energy as all of its particles put together. But when it squishes like this, now instead of the ball as an object moving, some of its particles move and they deform. Some of the energy is lost in that. I keep putting lost in quotes because remember, energy is never lost, but it changes into energy of the particles, which is also where we get this heat. It's almost completely immeasurable, but this increase in heat, a minuscule amount when we drop the ball. Most of the energy for this was lost as sound. So in theory, I mean hypothetically, a quieter ball would lose less energy. It would have to actually be the other way around. A ball that lost less energy would be quieter. Questions?